This is another reaction that carbonyls undergo in presence of a strong nucleophile. So we're still in the same concept where carbonyls react with strong nucleophiles. It's a strong because it's a negative. And that nucleophile is going to attack the partial positive charge carbon, break the double bond. But in this case, your product is going to be an alkene. This is a very useful reaction because Wittig reactions over here, they convert aldehydes or ketones. This is going to be our starting reactants into alkenes by using a reagent which we call a Wittig reagent. That Wittig reagent is made up of a phosphorus that has a positive charge that is connected by a covalent bond to a carbon with a negative charge. This is a carbanion. The phosphorus is connected to 3 phenyl groups. So this is why when we name the slide, we name it as a phosphorus light. The phosphorus light can be represented in 2 ways. It can undergo resonance to form the major resonance contributor. And the resonance always starts from the lone pair. So it's going to start from the carbanion, where the lone pairs add and form a double bond between the phosphorus and the carbon. These 2 representations are the same. Whenever you are doing whenever you are drawing the mechanism of this reaction, I would prefer that you use the charged form of the light because you can easily see your nucleophile in there. The reaction is going to proceed by replacement of the oxygen of the carbonyl. I didn't do anything to this carbon. This double bond stays. So I'm going to replace the oxygen of the carbonyl with whatever is connected to the phosphorus. So everything that is connected to the phosphorus, I'm just going to take it and put it in the place of the oxygen in there to get the alkene. Now, because I'm getting the alkene in there, and I know that alkenes have a stereochemistry, so here in this case, I can form, this is the limitation of this reaction, we can form E and Z isomers. And sometimes you don't want the E and Z, you just want one isomer in there. So this requires another additional step of purification in order to isolate the stereoisomer that you need. This is an example over here where I start with a ketone. This is the light. No matter what form of the light you use, whether it's a charged form or if it's a double bond form, you are replacing the oxygen with the CH2 in this particular example. So you're going to end up getting the alkene. In this particular example, you don't have E and Z. The whole idea over here is to prepare the phosphorus slide. And to prepare the phosphorus slide, we're going to do a 2-step reaction for that. We know that triphenylphosphine is a nucleophile. And this nucleophile is a good nucleophile, even though it's a neutral nucleophile, but it is a good nucleophile. This type of a nucleophile goes by an SN2 reaction. And we know that the conditions of SN2, whenever we want to use the alkyl halide, methyl halide works best. You can have a primary alkyl halide, but if you use a secondary alkyl halide, then this is going to act as a base. So you're going to end up getting some E2 elimination in there. You cannot use tertiary alkyl halide because with tertiary alkyl halides, you're going to end up not having a product because SN2 does not work with tertiary alkyl halide. So the reaction SN2 is a 1-step reaction. Nucleophile attacks the partial positive carbon. The halogen is going to leave. So in this case, what I did is I used the lone pairs of the phosphorus to make a bond between the P and the carbon. So the phosphorus lost electrons, so I would need to represent this in a form of a positive charge. Now, once you have this, you're not done yet because this is not your light. Your light is two charges, a charge on the phosphorus and a charge on the carbon. So now I want to introduce a negative charge on the carbon. To introduce a negative charge on the carbon, I need a base to take one of these hydrogens. So whatever is connected to the phosphorus should have a carbon with a hydrogen, because this is going to be our next step. The base that we normally use is a strong base. Any strong base can do the job. Most bases that we use are butyl lithium. This is an alkyl lithium in there. This is the organo lithium reagent. So this now acts as a base because I do have an acidic hydrogen. Remember what we talked about in chapter 16, that organo lithium and the Grignard reagents, they act as bases whenever you have an acidic hydrogen. If you don't have an acidic hydrogen, then they act as a nucleophile. So this one is going to act as a base. It's a butyl and the lithium in there. Another base that I can use is LDA. This is another base in there. I can also use bulky bases as well, potassium tertiary butoxide. In addition to LDA, both are bulky bases, and these can do the job. They can come, take the hydrogen, and form a negative charge on the carbon, and now this is the light. Light undergoes resonance. You can represent it in two forms. I would prefer that you choose this form and carry the rest of the mechanism. The mechanism you're responsible for, from the point where you start prepping for your light until you take your light and now react it with the carbonyl. So once you prepare your light in there, you're going to start reacting it with the carbonyl by using the same rules as we explained. So locate where is your most reactive carbon, which is your electrophilic carbon. And this is going to be my electrophilic carbon. So the nucleophile now, I can easily spot that this is a nucleophile in there. That nucleophile is going to come and attack the partial positive carbon. Every time I make a bond, I break a bond. Remember this. So when I do this, then I'm going to end up having an O negative charge in there. That negative charge is going to be so close to the phosphorus because the phosphorus is still having a plus charge in there. So now I'm going to create an intermediate. That intermediate, we call it an oxaphosphetane. It's fine, you don't have to memorize the name in there, but this intermediate is very unstable. The reason why it's unstable because you are making a cycle of four-membered rings in there. The reason why it's unstable because you are making a cycle of four-membered ring in there, and those membered rings are not carbons, they are electronegative elements, oxygen. So bonds between carbon and electronegative element are the ones that are going to break. Breaking this bond, the electrons of this bond are going to form a double bond between the carbon and the CH2, and this is going to be your product in this case. And then the bond between the C and the O is going to break, and you're going to form a double bond between the phosphorus and the oxygen. This is going to be your byproduct. And this byproduct, we call it a triphenylphosphine. Triphenylphosphine is very polar. In this type of experiment, normally we do a TLC and we spot the triphenylphosphine on the TLC. When we develop the TLC, the triphenylphosphine, because it's very polar, it's not going to migrate up the TLC plate. It's going to stay in its position because it is very polar and it bonds to the silica of the TLC. Going here. So let's have this example. You are starting with your aldehyde and you're reacting this with the phosphorus slide. I am showing the light in its major contributor resonance form. No charges on the carbon and on the phosphorus in there. And you want to get the product, and then you want to prepare the light and draw the mechanism of the reaction. So let's go ahead and do the product first. So you highlight the oxygen, and you replace the oxygen with all the group that is connected to the phosphorus. So everything that is connected to the phosphorus except the double bond, you simply take that, together with its carbon. Okay, so you're taking a cycle of 6-membered rings in there, and you are putting it in the place of the oxygen. So I have a carbon now, and then I have a cycle of 6-membered rings, and they're directly connected. So this is going to be my carbon in there. Okay, so this carbon is this carbon over here. So all I did is I replaced the oxygen with the R group that is connected to the triphenylphosphine. Let's go ahead and start with the mechanism of the reaction. The first step, which is going to be step 1, is going to be the lye preparation. So let's go ahead and prepare the lye in there. So to prepare the lye, it is a 2-step reaction. The first step, we're going to always start with the triphenylphosphine. This is going to be our nucleophile in there. So this is going to be our strong nucleophile, even though it is neutral, but the phosphorus is going to increase the nucleophilicity of this nucleophile in there. So this is why we are considering this nucleophile a strong nucleophile. We are going to react it with an alkyl halide. Now, if you notice, the R group that I have here is going to be my cyclohexane that is going to be connected to an X group. Let's say, for example, a bromine. Just go ahead and stick a bromine in there. This is a secondary alkyl halide. It still can go with SN2 reaction. It's not favorable to go with SN2 reaction, just SN2. It goes with both SN2 and E2 reactions, but the reaction can still happen. You're going to get some elimination, but you can isolate the product that you need and move on with the mechanism. So this one over here is going to be a secondary alkyl halide. The reaction is going to proceed by SN2 and E2 in there. I'm not going to write the E2 product. I'm going to neglect the E2 product. I'm just going to write the SN2 product. So the nucleophile, this is how I want you to answer this question when you're asked about the mechanism. Please show your arrows. Okay, so the lone pairs are going to attack the carbon. The bromine is going to leave. This is an SN2 one-step reaction. And you will be forming your triphenylphosphine in this case. Here you go. Now the phosphorus is going to be a positive charge because the phosphorus lost its electrons to make a bond between itself and the carbon. We are going to end up getting our E2 product in there, which is the cyclohexane. This one is going to act as a base. Base is going to come, take the beta hydrogen, form a double bond. The bromine is going to leave, but we are going to neglect the E2. I'm not going to show it. So now we're going to take our SN2 product in the second step, and we're going to react it with the base in order to make the lye. Remember that the lye is 2 charges. A charge on the phosphorus and a charge on the adjacent carbon. So this is going to be the adjacent carbon in here that is going to have a hydrogen. It needs to have a hydrogen so that we are going to react this with butyl lithium in there. So this is going to be our butyl lithium. This is going to be a base. And that base is going to come. Is going to take the hydrogen and form a negative charge on the carbon. So you're going to end up getting your lye. I would prefer to represent the lye again in the form of its charges so that you would see where is your carbanion that is going to add to the carbonyl. So that is going to be our phosphorus lye. Once you are done from the preparation of the lye, now in the third step, you are going to react with the carbonyl. So you're going to react the lye with the carbonyl, and this is going to be our third step. So we're going to go and check that our carbonyl is an aldehyde. So use the aldehyde and react this with the lye that you just made. Your mechanism needs to make sense. Your arrows need to make sense in there. So my nucleophile is this carbon over here. This carbon is going to come and attack the partial positive charge carbonyl. It's a reaction between a nucleophile and an electrophile in there. The bond is going to open and form a negative charge on the oxygen. So I'm going to end up getting my complex in this case. I'm very careful with these reactions not to add any extra carbon. So this is going to be my carbon. The carbon of the carbonyl is not on the cycle. So don't do this mistake in there. You have the carbon, which is a carboxylic carbon in this case. It's out of the cycle. So you have that over here. It's going to be a negative charge. All what you did is a bond between the carbon of the carbonyl and this carbanion in there. So we're going to create our new bond. This is the new bond that we are making. And that new bond is going to connect with the cycle in there. And coming right off the cycle is the triphenylphosphine. Okay, so now you can see that you have a close proximity of these charges. These charges are really close to each other. Because they are very close to each other, there will be a reaction in there because this is an electrophilic site. This is a nucleophilic site. So it makes sense that there will be a reaction between both, and I will create a bond between the oxygen and the phosphorus. So I'm going to make a bond in there between the oxygen and the phosphorus. Here you go. Don't add carbons again. And keep a track of the cycles that you are using in there. So once I have this, now I'm going to go ahead and search for my weak bonds. And the weak bonds are the bonds between the carbon and the electronegative element. These are my weak bonds. So now the weak bonds are going to go ahead and break. You're going to form a double bond in here, and you're going to form a double bond in there. This is going to be the intermediate. This is the oxaphosphatane, which is very unstable. And this one is going to form our product in this case. So our product is going to have a double bond in there. And then you're going to have a cycle of 5-membered rings. Alkene. My alkene here does not have any stereoisomers. It's neither cis nor trans because it has two groups that are the same. Plus my byproduct, which is the triphenylphosphine oxide, which is extremely polar. Let's have another example over here. So starting with this compound, okay, so it's going to be my first step in here. My first step, I am going to use the triphenylphosphine. My second step, I'm going to use the butyl lithium. And my third step, I'm going to use, let's say, acetone. Okay, let's draw acetone over here, which is the carbonyl. This is the simplest form of ketone. This is how you're going to see this reaction in there. And in this reaction, it's a 3-step reaction. All I need is my alkyl halide. So I forget about the ester. Okay, don't be confused about the ester. The reaction is going to be with the alkyl halide because my first step is that the carbonyl of the forget about the ester. My first step is going to be the carbon of the alkyl halide. This is the partial positive charged carbon in there. And that partial charged carbon is going to react with the triphenylphosphine by an SN2 reaction. So the triphenylphosphine is going to come, attack that carbon, form, because this is a primary alkyl halide, so the reaction can go easily by an SN2 reaction. So let's go ahead and divide the steps in here. So the first step with the triphenylphosphine, my SN2 reaction is going to happen, and I'm going to replace the bromine by the triphenylphosphine. I'm going keeping the same number of carbons in there, but now the bromine is being replaced by the triphenylphosphine, and the phosphorus will be a positive charge. My second step is the butyl lithium, and that is going to be my butyl group over there, together with the lithium, which is a plus a charge. Please pay attention to the carbons that you are working with. Here I have 4 carbons in there. And in this reaction, it's a base. That base is going to take the hydrogen, the acidic hydrogen, and form a negative charge on the carbon to create the carbonyl. So you're going to end up having your double bond O. You can have the base take the hydrogen, form a double bond in here, then that will be the other form of the light. Whatever you want, but it's easier for me to represent the light and its charges. So this is why I'm forming a carbonyl in this case. So you have your ethyl, the 2 carbons in here. Now this carbon is going to be a negative charge, and then I'm going to end up having a plus a charge on the phosphorus and the triphenyl. Now this is going to be my light. So you made your light in this case. Now, after you make your light, now we're going to go ahead and react the light with the acetone. So to react the light with the acetone, all what you need to do is check what R is connected to the phosphorus. So to the phosphorus, I have this carbonyl, everything in there. So I have this whole thing in there. So you're going to take the oxygen, and you are going to replace it with this whole thing. And your product in this case is going to be, let's draw the side first. So I have a carbon with 2 CH3s coming of it. And then I have a double bond. Okay. Now go ahead and draw your carbons. I have 2 carbons in there. I need to count this. So this is a carbon, because right now when I took the oxygen, I have nothing here. So I need to put a carbon in here. Okay, so this is going to be a carbon. Let's put a carbon in there. So that is going to be my first carbon. And this is going to be my second carbon. And then on that second carbon, I have a carbonyl. And then I have my O ethyl in there. Don't add more carbons than what you should. I have 2 carbons. This is my carbon over here. This is my carbon in there. Again, whenever I take the oxygen out, this side over here is going to be empty. So I have to fill it out with this carbonyl in this case. And this is going to be my product. Again, my alkene in this particular example is neither cis nor trans, because I do have 2 groups that are the same on the same carbon. Let's have another example. So again, this one is a primary alkyl halide. To break down the reaction, the first step is a simple SN2 reaction. You're having the nucleophile, the triphenylphosphine, and that the triphenylphosphine is attacking the partial positive charge carbon. The bromine is going to leave, so it is going to be a substitution reaction. You're having your phenyl, your 2 carbons in there. You created a bond between the carbon and the phosphorus. This is positive charge, and then the 3 phenyl in there. The second step, you are using a base, which is the butyl lithium. That is going to be a base. And the base is going to take the acidic hydrogen over here. So the hydrogen that it is going to take is the hydrogen that is directly connected to the phosphorus. So this one over here, this is the carbon, because after all, I'm going to form a negative charge on this carbonyl. Not this one. This one's going to be very far. This hydrogen is an acidic hydrogen. Why it's an acidic hydrogen? It's an acidic hydrogen because it's close to the phosphorus. And the phosphorus pulls electrons away from this hydrogen, make it partial positive. So this is why the base is going to come and take this hydrogen and form a negative charge on the carbon. In this example, you are going to form the two stereoisomers, the E and the Z. So now I'm going to form my carbon ion in this case and my positive charge on the phosphorus, which is already there. So that is going to be the light. So always the first step, the first two steps are going to make the light. Once you make the light, you can react it with the carbonyl to get the alkene. So now we're going to go ahead and react it with the carbonyl in there. If I didn't ask you about the mechanism, you don't have to show the mechanism of any of those steps in there. But it's really helpful, you know. But for here, you don't have to show the mechanism of the reaction. You can simply replace, as we mentioned, the oxygen with the group that is connected to the phosphorus. So starting from the carbon ion and all the way over here. So this is the whole thing that is going to replace the oxygen. Pay attention to your alkene because here I'm going to end up having stereoisomers in this case. So I have a carbon, I have a double bond. Now on that carbon, I'm going to end up having this carbon over here. And this carbon is connected to a carbon and to a phenyl group. Okay, I do have a hydrogen over here. Now on this carbon, I have a phenyl group. You can simply write it as a phenyl group. This is the phenyl group. So on this carbon, I have the phenyl and I do have the hydrogen. This is the Z isomer. Okay, I can also have the E isomer. Let's go ahead and draw the E isomer there, where you're going to have the two carbons. Let's keep this in its place there. Hydrogen, let's put the phenyl over here, and then a hydrogen, and this is going to be the E isomer. So for this particular example, I got two stereoisomers. I got the Z and I got the E stereoisomer. Now, let's say, for example, if you are given an alkene and you are asked to go ahead and prep that. So all what you need to do now, remember how we did the double bond? We did the double bond by a combination between a carbonyl and the lide. So you're going to break it down and have one side to be the carbonyl and the other side to be the lide. If you can make the side of the lide to be a primary carbon, go ahead and do that. Because after all, the lide is going to come from a primary alkyl halide. So this side over here, this carbon, I can stick a bromine to and the hydrogen to in there. So you're going to add a hydrogen and add a halogen. We're adding a hydrogen because remember, in the second step, we're going to use a base in order to take that hydrogen out. So you add the hydrogen and the bromine to this carbon, and you add an oxygen to this carbon over here. This side is better to be the lide rather than the other side. If you stick a bromine in here, it's going to be a secondary alkyl halide. So it's going to be a slower reaction, a slower SN2 reaction than this one. So now once you get your carbonyl and your alkyl halide, you can go ahead and you react this with triphenylphosphine and with the butyl lithium. It create the lide, and then the lide can react with the carbonyl to get the product.